The water is still. Here, in the vast, shallow reaches of the Middle Ordovician, the light of a distant sun filters through the surface in long, shimmering curtains of pale green and gold. There are no breaking waves to be heard, only the soft, rhythmic displacement of water. This is a world defined by the cradle of the epicontinental seas, shallow oceans that have spilled over the edges of the ancient continents, turning the interiors of the land into a submerged sanctuary. The silence is profound. It is a quiet that has existed for millions of years, held within the weight of the sea. The seafloor below is a mosaic of carbonate sands and soft, silty plains. It is a landscape shaped by the slow accumulation of minerals, where every grain of sediment is a record of time passing in the deep. The water is warm, cradled by a stable climate that knows no winter. In this warmth, the chemistry of the ocean is perfectly balanced, saturated with the calcium and carbon necessary for life to build its monuments. There is a sense of immense, unhurried growth. The currents here are not drivers of chaos, but gentle carriers of nutrients, moving with the slow deliberation of the tides. As we drift across this submerged expanse, the scale of the Ordovician world becomes clear. The horizons are boundless, stretching away into the hazy blue-grey of the deep shelf. There are no forests on the land above, no sounds of wind in the trees. All the energy of the planet is concentrated here, beneath the surface. The atmosphere of the ocean is thick with the presence of life that does not rush. It is a slow-motion ballet of biological existence, where the passage of a day is marked only by the subtle shifting of the light and the steady pulse of the tides against the carbonate banks. In this chapter of the Earth's history, the geography is unrecognizable. The great land masses of Laurentia and Baltica sit low in the water, their edges blurred by the encroaching seas. These are the nurseries of the ancient world. The water column is a vast, three-dimensional gallery filled with the suspended forms of microscopic life that fuel the entire ecosystem. It is a world of clarity. Because there are no terrestrial plants to shed soil into the rivers, the oceans remain transparent, allowing the sun to reach depths that nourish the very floor of the sea. We move deeper into the basin, where the pressure increases with a comforting, steady weight. The colours shift from the vibrant teal of the shallows to a deeper, more meditative indigo. In this space, the environment is constant. The temperature does not fluctuate, the salinity remains even. It is the perfect laboratory for the emergence of giants. Here, the laws of physics and the abundance of resources have aligned to support a new kind of existence. The stage is set for a form that is both elegant and massive, a creature of geometry and grace that will soon define the peak of this ancient marine hierarchy. The floor of the basin is alive with the subtle movements of the benthos. Small, trilobite-like forms move through the silt, their carapaces clicking softly against the stones, a sound lost in the vastness of the water. Sponges and primitive corals anchor themselves to the hard ground, filtering the water with a patience that spans generations. Everything in this world operates on a different scale of time. There is no urgency, only the enduring rhythm of the sea. This is the dawn of the age of the cephalopod, a time when the straight-shelled wanderers begin their long, silent reign over the global interior. We are drifting now, caught in a current that pulls us toward the heart of the Ordovician basin. The light is fading slightly as we descend, but the water remains clear, revealing the vast architecture of the seafloor. It is a kingdom of limestone and life, a place where the foundations of the future are being laid in the quiet dark. The water feels thick, supportive, and ancient. It is the beginning of a story written in the stone of the seabed, a story of a giant that moved through these waters with the weight of the world on its back and the stillness of the deep in its heart. In the quiet transition of the early Ordovician, a new architectural form began to appear within the lineage of the cephalopods. Evolution moved with the same slow, deliberate pace as the deep-sea currents, refining a design that would eventually reach its peak in the massive frame of Cameroceras. To understand the giant, one must first understand the geometry of its origins. The ancestors of these creatures were smaller, often curved and bound to the seafloor. But the pressure of life and the pull of the open water invited a transformation. The shell began to straighten, lengthening into a perfect tapering cone known as an orthocone. This shift from a curved shell to a straight one was not merely a change in appearance, but a masterwork of biological engineering. By aligning the chambers in a single, linear row, the orthocone achieved a level of stability and hydrodynamic efficiency previously unknown in the ancient seas. This was the birth of the endocerid lineage. Fossil evidence preserved in the oldest limestone layers reveals these early experiments in form. Shells no longer than a human hand, yet possessing the same fundamental internal structures that would one day support a creature the size of a ship's hull. The straightening of the shell allowed for a new relationship with gravity. As the animal grew, it moved forward, sealing off the space behind it with a thin, mineralized wall called a septum. This created a series of hollow rooms, a biological record of the animal's history. In these early ancestors, we see the first evidence of the siphuncle, the living cord of tissue that linked every chamber back to the animal's heart. This cord was the secret to the orthocone's success, allowing it to manipulate the gases within its shell and rise, for the first time, away from the dust of the sea floor. The fossil record of this period is a silent gallery of these emerging forms. In the strata of what is now the Baltic region and North America, we find the delicate remains of Protoplastoceras and other early nautiloids. They are the blueprints. Their shells show a gradual thickening of the walls and a widening of the internal piping, adaptations necessary to survive the increasing pressures of deeper water. There is no drama in this transition, only the steady, persistent work of natural selection, crafting a vessel that could navigate the three-dimensional vastness of the water column. As the millions of years drifted by, the orthocone design proved to be exceptionally resilient. The straight shell provided a natural defense, a hard carbonate fortress into which the soft body could retract at the slightest vibration in the water. But more importantly, the straightness allowed for larger growth. Without the mechanical constraints of coiling, the shell could extend indefinitely, provided the animal could maintain its balance. This was the evolutionary path that led directly to the giants. The small, drifting ancestors with a quiet prologue to a much larger story. In this chapter of time, we see the ocean testing the limits of this new anatomy. The water remains the great architect, providing the calcium carbonate that the cephalopods harvested from the sea to build their lengthening homes. Each new generation of orthocones grew slightly larger, their siphuncles slightly more robust, their buoyancy control more refined. They were becoming the masters of the midwater, neither rising to the surface nor sinking to the mud, but suspended in a perfect, weightless equilibrium. The genesis of the orthocone was a triumph of mathematics and biology. It was the moment the cephalopod broke its tether to the bottom and claimed the volume of the sea. As we look at these early fossils, we see the unmistakable silhouette of what is to come. The long, elegant taper of the shell is a promise of the massive Cameroceras that will eventually patrol these same waters. The foundation has been laid in the ancient stone, the straight line has been drawn through the water, and the era of the great nautiloids has truly begun. The majesty of Cameroceras is held within its shell, a vast, rigid monument of calcium carbonate that protected the life within and allowed it to endure. This structure was not a static object, but a living extension of the animal, built molecule by molecule from the very chemistry of the Ordovician Sea. The water of this era was rich in dissolved aragonite, and the mantle of the cephalopod acted as a tireless architect, harvesting these minerals to create a tapering fortress. This chapter focuses on the slow, crystalline growth of the orthocone's primary defense. The shell was composed of several distinct layers, each serving a specific mechanical purpose. The outermost layer was dense and porcelain-like, designed to deflect the impact of debris or the grasp of a rival. Beneath this sat the nacreous layer, or mother of pearl. This layer consisted of thousands of microscopic plates of aragonite, stacked like bricks and bound by thin sheets of organic proteins. This staggered arrangement gave the shell its incredible strength, allowing it to withstand the crushing weight of the deep water without fracturing. It was a material both hard and resilient, a testament to the sophistication of ancient biology. The growth of the shell was an unending process. As the animal matured, the mantle secreted new material at the leading edge, slowly extending the cone forward. This growth was not uniform, but occurred in rhythmic pulses, perhaps influenced by the availability of minerals or the cycles of the ancient moon. These pulses are preserved in the fossil record as delicate growth lines, similar to the rings of a tree. By examining these lines, we can see the history of a single individual's life, periods of rapid expansion, followed by moments of slow, steady maintenance in the quiet dark. One of the most remarkable features of the Cameroceras shell was its internal geometry. As the shell lengthened, it became increasingly heavy. To prevent the animal from becoming a prisoner of its own weight, the shell was engineered to be hollow. Only the very front, the living chamber, held the soft tissues of the animal. The rest of the shell was a hollow, pressurized vessel, a series of airtight rooms that provided the buoyancy needed for the animal to remain suspended. The shell was not a burden, but a sophisticated flotation device. The chemistry of the shell also served as a biological archive. During the Ordovician, the oceans were in a state of calcite sea chemistry, but nautiloids like Cameroceras were specialized in secreting aragonite, a more soluble form of calcium carbonate. This required a significant investment of metabolic energy. The animal had to constantly process the surrounding seawater, concentrating the ions within its body before laying them down as solid stone. This process was a silent, chemical labor that lasted for decades, resulting in a structure that could eventually reach the length of a modern bus. As we visualize the shell in its original state, it was likely smooth and perhaps marked with subtle, neutral patterns that helped it blend into the shimmering light of the water column. It was a masterpiece of paleontology, a straight, elegant needle of stone drifting through an endless blue. Over time, as the animal died and settled into the silt, the organic proteins would vanish, leaving only the mineralized cone to be filled with fine sediment. It is this mineral ghost that we find today, a heavy, stone reminder of a creature that once lived a life of weightless grace. The shell of Cameroceras was more than a home. It was the boundary between the organism and the infinite sea. It provided the structure for its muscles, the protection for its organs, and the physics for its movement. In the stillness of the Ordovician deep, the slow accretion of carbonate was the heartbeat of the species. Through millions of years of geological pressure, these shells have endured, transitioning from living tissue to solid rock, preserving the exact dimensions of a giant that the world will never see in the flesh again. Within the long tapering corridor of the shell, Cameroceras possessed a series of internal walls known as septa. These partitions were not merely dividers, they were the structural ribs that allowed a creature of such immense length to survive the crushing embrace of the deep ocean. Each septum was a concave disc of nacre, curved like a shallow bowl to distribute the external water pressure evenly across the shell's surface. Without these internal supports, the hollow cone would have imploded under the weight of the sea. The formation of a new septum was a rhythmic event in the life of the cephalopod. As the animal's soft body grew too large for its current space, it would move forward toward the opening of the shell. Once in its new position, the rear mantle would begin the slow, silent work of secreting a new wall of aragonite behind it. This process effectively sealed off the previous living space, transforming it into a new, airtight chamber within the phragmocone. These chambers were the silent milestones of the animal's maturity, each one marking a specific period of growth in the ancient dark. The spacing between these septa was remarkably consistent, reflecting a precise biological blueprint. In the fossils of Cameroceras, we see these divisions as a series of repeating lines that run the length of the specimen. Each chamber was a vacuum-sealed vault, connected to the rest of the shell only by the passage of the siphuncle. The integrity of these walls was a matter of survival. A single breach in a septum could lead to a loss of buoyancy, causing the giant to sink helplessly toward the seafloor. Engineering-wise, the curvature of the septa was a masterpiece of physics. By being convex toward the rear and concave toward the living chamber, the septa acted as arches. In the same way that an arch supports the weight of a stone cathedral, these mineralized walls supported the weight of the Ordovician column. This allowed Cameroceras to explore deeper into the basin than many of its contemporaries, patrolling the dim, high-pressure zones where the sunlight barely reached. Where the septum met the inner wall of the shell, it formed a contact line known as a suture. In Cameroceras, these sutures were simple and straight, a characteristic of the early nautiloid groups. These lines, though simple in appearance, represent the fusion of the internal skeleton with the external armor. In the fossilized remains we find today, the outer shell has often eroded away, leaving the pattern of the septa exposed like a stack of nesting cups. This reveals the internal rhythm of the animal's life, frozen in stone. As the animal drifted, the septa provided the necessary rigidity to keep the long shell from flexing or snapping during movement. They turned a fragile tube into a reinforced pillar. The interior of the shell was a place of perfect order, a series of dark, silent rooms that held nothing but gas and the thin, living thread of the siphuncle. It was a cathedral of carbonate, built to endure the vast pressures of a world that existed long before the first mountains were raised. The study of these internal walls allows us to understand the mechanical limits of prehistoric life. The thickness and curvature of the septa in Cameroceras suggest an animal built for stability and depth. It was not a creature of the turbulent surface, but a resident of the calm, pressurized layers of the sea. The septa are the silent witnesses to that endurance, preserving the exact geometry of a life that was lived in a world of constant, heavy stillness. Running through the center of every chambered room within the shell was a single, continuous thread of life, the siphuncle. In Cameroceras, this organ was not a delicate filament, but a robust, calcified tube that served as the biological engine for the entire organism. It was the only living tissue that extended back from the head into the farthest reaches of the ancient shell. This chapter explores the silent chemical work of this vital conduit, which allowed a creature of stone to become a creature of flight within the water. The siphuncle was the primary tool for hydrostatic regulation. It was a complex bundle of blood vessels and specialized cells, enclosed in a porous, mineralized sheath. Its purpose was to move fluids in and out of the chambers of the phragmocone. By utilizing a process of osmotic pumping, the siphuncle could remove seawater from a newly formed chamber and replace it with a low-pressure gas, primarily nitrogen. This was a slow, energy-efficient process that allowed the animal to adjust its weight relative to the water around it. In Cameroceras, the siphuncle was exceptionally large, sometimes occupying a significant portion of the shell's diameter. This size suggests a highly efficient system for managing the massive volume of the shell. Within the tube, the animal's blood would flow, carrying ions that created a salt gradient. This gradient drew moisture through the porous walls of the siphuncle and into the circulatory system, leaving a vacuum in the chamber that was eventually filled by gas diffusing from the blood. It was a quiet, internal tide that governed the animal's existence. The position of the siphuncle was equally important. In this genus, it was located ventrally, or along the bottom edge of the shell as the animal drifted. This placement acted as a stabilizer. Because the siphuncle and its associated mineral deposits were heavier than the gas-filled chambers, they provided a natural ballast. This ensured that the shell remained in a horizontal orientation, preventing the animal from spinning or bobbing uncontrollably. The siphuncle was both a pump and a keel, providing the physical balance necessary for a long-distance drifter. Beyond buoyancy, the siphuncle served as a sensory link to the rest of the shell. Though the chambers themselves were empty of life, the siphuncle could detect changes in pressure or internal chemistry. If the shell were to suffer a hairline fracture, the siphuncle would respond by attempting to seal the area with new mineral deposits or by adjusting the fluid levels to compensate for the leak. It was a self-healing system, a living maintenance crew that operated in the dark, silent voids of the orthocone. As Cameroceras moved through different depths of the Ordovician Sea, the siphuncle worked tirelessly to maintain equilibrium. The deeper the animal descended, the greater the external pressure became, and the more the siphuncle had to regulate the internal gas pressure to prevent the septa from collapsing. It was a constant, microscopic battle against the weight of the ocean. This labour was invisible and silent, a slow chemical rhythm that supported the massive weight of the predator as it patrolled the dim edges of the continental shelves. The siphuncle is often the most well-preserved part of the Cameroceras fossil, sometimes remaining as a solid stone rod even after the outer shell has weathered away. These siphuncular casts are the most common evidence we have of these giants. They represent the core of the animal's identity, the bridge between the living soft body and the mineralized fortress. It was the siphuncle that gave Cameroceras its mastery over the vertical world of the sea, allowing it to drift through the millions of years with the effortless grace of a cloud. In the vast, three-dimensional world of the Ordovician Sea, Cameroceras existed in a state of near-perfect weightlessness. This condition, known as hydrostatic equilibrium, allowed a creature of immense mass to remain suspended at any depth without the need for constant, exhausting movement. For a giant with a shell reaching several meters in length, the laws of physics were both a challenge and a tool. This chapter explores the delicate balance between the downward pull of gravity and the upward force of buoyancy that defined the life of the orthocone. The fundamental principle governing this equilibrium is buoyancy. According to the laws of fluid dynamics, an object submerged in water is pushed upward by a force equal to the weight of the water it displaces. For Cameroceras, the primary challenge was the heavy calcium carbonate of its shell, which was significantly denser than seawater. Without a counteracting force, the animal would have sunk rapidly to the benthos. To solve this, the animal utilized its gas-filled chambers as a series of biological balloons, creating an upward lift that precisely neutralized the weight of its mineralized armor. Achieving this balance required meticulous internal management. If the animal was too light, it would float uncontrollably toward the surface. If too heavy, it would struggle to stay off the seafloor. Cameroceras maintained neutral buoyancy by keeping its shell roughly 90% gas and 10% fluid. The gas, mostly nitrogen, was held at a pressure lower than the surrounding sea, providing the necessary lift. This state of equilibrium meant that the giant could hover in the water column, expending almost zero energy to maintain its position, a vital adaptation for a predator of its scale. The distribution of weight was just as critical as the amount of lift. Because the living animal resided in the very front of a long, straight cone, the shell had a natural tendency to tip or pitch. To remain horizontal, Cameroceras evolved a system of ballast. As the siphuncle moved fluids through the chambers, it often left behind mineral deposits known as cameral deposits in the oldest, smallest chambers at the rear of the shell. These deposits acted as a counterweight, pulling the tail of the shell down to level it with the heavy head. This created a stable, horizontal platform from which the animal could scan the environment. This equilibrium was not static, it was a dynamic, lifelong process. As the animal grew and added more weight to its living chamber, it had to simultaneously create new gas chambers and adjust its internal ballast to compensate. This was a slow-motion adjustment that occurred over weeks and months. Cameroceras was not a creature of rapid vertical migrations. It did not zip between the surface and the deep like modern squid. Instead, it moved through the ocean with the slow, majestic pacing of a cloud drifting through the sky, governed by the subtle shifts in its internal chemistry. In the stillness of the deep shelf, this weightlessness transformed the giant into a silent observer. With its buoyancy perfectly trimmed, it could drift with the prevailing currents, its tentacles trailing behind or tucked neatly against its head. It became a part of the water itself. This mastery of physics allowed Cameroceras to reach sizes that would have been impossible for a bottom-dwelling creature. By conquering the weight of its own shell, it became the undisputed master of the Ordovician water column, a testament to the power of biological engineering. The legacy of this equilibrium is visible in the fossils we find today. Many Cameroceras specimens are found in a horizontal position within the strata, reflecting the posture they held for decades in life. They remind us that the ancient oceans were not just a place of struggle, but a place of perfect, calculated balance. The orthocone was a creature of precision, a living instrument tuned to the density of the sea, existing in a state of grace that allowed it to dominate its world through the simple, quiet mastery of gravity. While the vast majority of the shell was a hollow vessel of gas and stone, the very front of Cameroceras was home to the living animal. This final, largest section is known as the living chamber. It was a spacious, open-ended hall of aragonite where the soft, vulnerable tissues of the cephalopod were anchored. All the sensory organs, the digestive system, and the powerful muscles of the giant were contained within this single protected space. It was the command center of the orthocone, the interface between the living organism and the ancient sea. The interior of the living chamber was lined with a specialized layer of smooth, iridescent nacre. This provided a frictionless surface for the animal's mantle, the muscular organ that surrounded the internal systems. The mantle was firmly attached to the shell by a series of powerful muscles. In well-preserved fossils, the muscle scars are still visible, indentations in the stone where the tissue was once fused to the carbonate walls. These scars reveal the immense strength Cameroceras possessed, as these muscles had to support the weight of the soft body and control the movement of the tentacles and the hypernome. As a giant invertebrate, the internal organs of Cameroceras were likely arranged in a compact, efficient manner, typical of nautiloids. Behind the head lay the gills, which extracted oxygen from the slow-moving Ordovician waters. The digestive tract and the reproductive organs were situated toward the rear of the chamber, near the first septum. This placement ensured that the animal's center of mass remained as stable as possible. The living chamber acted as a biological cradle, protecting these vital systems from predators and the mechanical stresses of the environment. The opening of the chamber, called the aperture, was where the animal's head and appendages emerged. This was the most active part of the creature. The head was protected by a thick, muscular hood, similar to that of a modern nautilus. When the animal felt threatened or needed to rest, it could retract its entire body deep into the living chamber, using the hood as a door to seal the entrance. This turtle-like defense made Cameroceras nearly invulnerable to the smaller predators of its time, turning its home into a portable fortress. The dimensions of the living chamber changed as the animal aged. As Cameroceras grew, it didn't just add more chambers to its tail, it expanded the diameter and length of its living space. This was a continuous cycle of renovation. The animal would move forward, secrete a new floor behind it, the septum, and build more wall at the front. By the time it reached full maturity, the living chamber alone could be large enough to house a person, a cavernous space of shimmering pearl and living muscle drifting through the deep. This chamber also served as a sensory hub. The animal's large eyes were positioned at the edge of the aperture, allowing for a wide field of view. Above the mouth, specialized olfactory organs sampled the water for chemical traces of prey. The living chamber was the point where the animal's intent met the physical world. Every decision to move, to feed, or to descend was executed by the tissues housed within these mineralized walls. It was the only part of the shell that pulsed with the warmth and energy of life. In the fossil record, the living chamber is often found crushed or distorted, as it lacked the internal septa that reinforced the rest of the shell. However, when found intact, it provides the most direct connection to the animal as a living entity. It reminds us that Cameroceras was not just a geological curiosity or a hollow cone, but a breathing, sensing creature of the deep. It was a life lived in a house of stone, a silent inhabitant of the Ordovician vastness, perfectly centered within its own architectural masterpiece. In the dim, filtered light of the Ordovician seas, sight was a vital tool for navigation and survival. Cameroceras possessed eyes that were remarkably sophisticated for their time, allowing the giant to interpret the vastness of the water column. Unlike the complex lenses of modern fish, which had not yet evolved to dominate the sea, The eyes of this nautiloid operated on the principle of a pinhole camera. This chapter explores how these sensory windows allowed the orthocone to perceive its world in a slow, steady stream of visual data. The eyes of Cameroceras were positioned on either side of its head, providing a wide, nearly panoramic view of the surrounding ocean. These eyes lacked a solid lens. Instead, they featured a small opening that allowed light to pass through a tiny aperture and project an image onto the retina. This design meant that the image was not as bright or as sharp as a modern eye, but it was highly effective for detecting movement and silhouettes against the shimmering surface light. To a Cameroceras, the world appeared as a soft, high-contrast landscape where every shadow held a potential meaning. This visual system was perfectly tuned to the light levels of the deep shelf. In the shallow, sunlit waters, the pinhole eye could resolve the shapes of drifting trilobites and the outlines of coral thickets. As the animal descended into deeper, darker layers, its pupils could likely dilate slightly to capture more of the fading light. Because the water was clear and free of terrestrial runoff, the giant could see for significant distances, spotting the rhythmic pulses of other cephalopods or the slow movement of benthic life from several meters away. The placement of the eyes allowed for excellent peripheral vision, which was crucial for a creature with a long, inflexible shell. While Cameroceras could not easily turn its entire body to look behind it, its eyes were angled to cover the flanks. This ensured that the animal was always aware of its surroundings, even as it drifted forward with the current. This constant vigilance was not born of fear. There were few threats to a creature of this size, but was instead a requirement for locating its own food sources within the immense volume of the sea. In addition to detecting light and shadow, the eyes likely helped the animal maintain its horizontal orientation. By tracking the gradient of light, which was always brightest toward the surface, the cephalopod could verify its position in the water column. This visual feedback worked in tandem with the physical balance provided by the siphuncle and the cameral deposits. The eyes were the sensors that confirmed what the body already felt, a state of perfect, weightless suspension in the blue. As the sun set over the Ordovician horizon, the visual world of Cameroceras would shift. Bioluminescence from smaller marine organisms might have provided pinpoints of light in the dark, and the giant's eyes would have been sensitive enough to track these movements. The night was not a time of blindness, but a different kind of seeing. The predator remained active, its pinhole eyes scanning the gloom for the subtle disruptions in the water that signaled the presence of its next meal. The vision of Cameroceras was a reflection of the Ordovician itself, measured, steady, and clear. It was a sight without the frantic flickering of modern life, a way of seeing that matched the slow, geological pace of the ancient oceans. Through these eyes, the giant witnessed the quiet expansion of the marine world, watching the slow-motion evolution of the seafloor from a vantage point of silent, drifting authority. Emerging from the circular opening of the head was a ring of muscular tentacles, the primary tools for both sensing and interacting with the Ordovician environment. Unlike the suckered arms of a modern octopus, the tentacles of Cameroceras were numerous, slender and flexible, more akin to those found on a modern nautilus. They formed a sensitive, tactile crown around the mouth, acting as the animal's primary interface with the physical world. This chapter explores the function of these appendages in a world without hands or complex limbs. The tentacles, often referred to as cirri, were composed of densely packed muscle fibers that allowed for precise, fine-tuned movements. In Cameroceras, these limbs could be extended far into the water column to probe for obstacles, or retracted completely within the protection of the living chamber. Each tentacle was covered in a specialized sheath of skin, but they lacked the chitinous hooks or suction cups seen in later cephalopod lineages. Instead, they relied on a powerful grip and a high degree of coordination to manipulate objects and secure food. Beyond their role in grasping, the tentacles were highly sophisticated sensory organs. They were lined with thousands of chemoreceptors, allowing Cameroceras to taste the water as it drifted. This chemical sense was essential for identifying prey and detecting the presence of other cephalopods across vast distances. By waving its tentacles in the slow-moving currents, the giant could pick up the microscopic chemical trails left behind by a passing school of smaller organisms, following the scent with a patient, predatory focus. The arrangement of the tentacular ring was designed for efficiency. The tentacles were grouped into distinct clusters, with some specialized for sensing and others for the heavy work of capturing and holding prey. This division of labor allowed the animal to maintain a constant sensory perimeter while its primary limbs were occupied. As it drifted above the seafloor, the tentacles would often dangle downward, likely brushing against the tops of crinoid gardens or feeling the vibrations of trilobites scurrying through the carbonate mud below. When prey was located, the movements of the tentacles were rhythmic and sure. They would envelop the target in a cage of muscle, pulling it inward toward the central mouth. Because the tentacles were so numerous, the animal could maintain a firm hold on even the most slippery or armored prey, such as the thick-shelled trilobites of the era. This capture was not a sudden, violent strike, but a methodical enclosure, a slow-motion entrapment that matched the unhurried pace of the Ordovician Sea. In the stillness of the deep shelf, the tentacles also served as a means of communication and social interaction. By touching the tentacles of another of its kind, a Cameroceras could likely exchange chemical and tactile information. This silent language of touch was the social fabric of the species, a way to navigate the immense solitude of the ancient oceans. The tentacular ring was the bridge between the animal's internal world and the external environment, a soft and sensing tool at the front of its rigid, stony home. As we visualize the giant in motion, the tentacles appear as a fringe of soft, moving life at the apex of the shell. They were constantly active, twitching and curling as they sampled the brine and searched for the next destination. They remind us that Cameroceras was a creature of immense sensitivity, a giant that felt its way through the world with a delicate, persistent curiosity. Through these limbs, the orthocone remained connected to the life of the sea, a silent observer and participant in the slow-motion drama of the prehistoric deep. At the center of the tentacular ring, hidden within the muscular base of the head, lay the primary feeding instrument of Cameroceras, a powerful two-part beak, composed of chitin, a tough, fibrous glucose derivative, and reinforced with mineral deposits. This beak was designed for the mechanical breakdown of the armored organisms that populated the Ordovician seafloor. While the animal lacked the complex teeth of later vertebrates, this singular tool provided all the force necessary to maintain its position at the top of the food chain. The beak of Cameroceras operated much like a pair of inverted shears. It consisted of an upper and lower mandible that overlapped, allowing the animal to exert tremendous localized pressure. This was particularly important in an era dominated by trilobites and brachiopods, whose bodies were protected by thick, calcified exoskeletons. The beak was capable of snapping through these defenses with a single, measured bite, reaching the soft, nutrient-rich tissues within. It was an instrument of precision, built to process the hardest materials the ocean could produce. The muscles that operated the beak were housed deep within the buccal mass, a dense sphere of tissue located just behind the mouth. These muscles were some of the strongest in the animal's body, anchored directly to the internal cartilage of the head. When feeding, Cameroceras would use its tentacles to position its prey precisely against the beak. The movement was not frantic, it was a slow, mechanical crunch, a rhythmic processing of energy that echoed the steady, unhurried nature of the predator itself. Inside the beak sat the radula, a ribbon-like tongue covered in rows of tiny chitinous teeth. Once the beak had breached the shell of a prey item, the radula acted as a rasp, shredding the soft tissue into small, easily digestible fragments. This two-step process, crushing followed by shredding, ensured that Cameroceras could extract the maximum amount of energy from every meal. In the nutrient-dense environment of the Ordovician, this efficiency allowed the giant to maintain its massive bulk while expending very little effort. The chitinous nature of the beak meant that it was rarely preserved as perfectly as the carbonate shell. While the shell became a stone monument, the beak often decayed or was scattered by currents. However, Rare fossil finds and comparisons with modern nautiloids allow us to reconstruct its form with great accuracy. The beak grew throughout the animal's life, with new layers of chitin added at the base to compensate for the wear and tear of crushing shells. It was a tool that was always sharp, always ready, and perfectly adapted to its role. In the silence of the deep shelf, the beak was the final destination for the energy of the ecosystem. It was the point where the life of the trilobite, or the smaller nautiloid, was transformed into the growth of the giant. There was no malice in this process, only the fundamental recycling of matter that has governed the oceans for eons. The beak was the silent engine of the predator's survival, a dark, hidden heart of strength at the center of the soft, tentacular crown. As we look at the anatomy of Cameroceras, the beak represents the culmination of its predatory design. The eyes located the target, the buoyancy allowed for a silent approach, the tentacles secured the hold, and the beak completed the cycle. It was a complete and harmonious system, a masterpiece of Ordovician biology that functioned with the reliability of a machine and the grace of a living creature. Beneath the suspended form of Cameroceras, the sea floor of the Ordovician was a vibrant, crowded tapestry of life. This was the era of the Great Ordovician Biodiversification Event, a time when the diversity of marine life exploded across the global seabed. The benthic environment, the world of the ocean floor, was not a wasteland, but a dense forest of calcified structures and soft-bodied organisms. This chapter descends into the quiet gardens of the deep shelf to meet the neighbours of the orthocone. The most striking feature of this ancient seabed was the abundance of crinoids, often called sea lilies. Though they looked like plants, these were animals, echinoderms related to modern starfish. They grew in vast, waving meadows, their long, segmented stalks anchored to the carbonate mud, while their feathery arms filtered nutrients from the passing current. These crinoid forests provided a complex, three-dimensional habitat for smaller creatures, creating a sanctuary of shadows where juvenile trilobites and gastropods could hide from the gaze of predators above. Shared among these meadows were the brachiopods, shelled animals that resembled clams but belonged to a distinct lineage. They blanketed the harder surfaces of the seafloor in the millions. Their shells, often ribbed or smooth, provided a stable foundation for other life forms, such as bryozoans, tiny colonial animals that built lace-like structures over any available surface. The seafloor was a place of constant competition for space, where every square inch of reef or rock was claimed by a filter-feeding tenant. Moving through the silt and between the crinoid stalks were the trilobites, the most recognizable inhabitants of the Ordovician. By this period, trilobites had evolved into a staggering array of forms. Some were blind scavengers that ploughed through the mud, while others possessed enormous wraparound eyes to watch for shadows from the water column. They were the primary movers of the benthos, recycling organic matter and serving as a fundamental link in the food web. Their rhythmic scurrying was the heartbeat of the seafloor. The environment was also populated by early corals and massive sponges. These organisms were the reef builders of the age, constructing low, mound-like structures called bioherms. Unlike the towering coral reefs of the modern world, these were subtle, sturdy mounds that stood only a few meters high. They acted as the structural anchors of the ecosystem, breaking the flow of the currents and creating pockets of calm water where delicate larvae could settle and grow. The reef was a slow-motion city, built over centuries by the steady secretion of calcium carbonate. From its vantage point in the water column, Cameroceras was the silent observer of this bustling world. The relationship between the giant and the benthos was one of predator and prey, but also one of balance. The waste produced by the cephalopod drifted down to nourish the filter feeders, while the abundance of the seafloor provided the energy needed to sustain the giant's growth. It was a closed loop of biological energy, governed by the slow cycles of the sun and the tides. As we visualize the Ordovician seafloor, we see a world of profound stability. There were no fish to dart through the water, no marine reptiles to disturb the peace. The benthos was a kingdom of invertebrates, a place where life moved at the pace of a growing crystal. It was a landscape of intricate beauty and geological endurance, a quiet, crowded world over which the shadow of the orthocone passed like a slow-moving cloud. The relationship between Cameroceras and the trilobite was the defining ecological intersection of the Ordovician seas. For millions of years, these two groups existed in a state of biological tension, a slow-motion pursuit between the master of the water column and the master of the seafloor. Trilobites were the most diverse and abundant prey available, and their evolution was often driven by the need to survive the attention of large cephalopods. This chapter examines the predator-prey dynamics that shaped the behavior and anatomy of both species. Trilobites were highly successful arthropods, protected by a three-lobed exoskeleton made of calcite and chitin. By the time Cameroceras reached its giant proportions, trilobites had developed a variety of defensive strategies. Some species, like Asaphus, possessed long eye stalks that allowed them to peer upward from the safety of the mud, watching for the silhouette of an orthocone. Others, such as the genus Cerorus, were covered in sharp, defensive spines that made them difficult for tentacles to grasp and painful for a beak to process. The hunting method of Cameroceras was likely one of patient hovering. Utilizing its perfect buoyancy, the giant would drift centimeters above the crinoid meadows, its tentacles hanging like a delicate net. When it detected the chemical signature or the mechanical vibrations of a moving trilobite, it would slowly lower its mass. There was no need for a high-speed chase. The trilobite's defense was its armor, and the cephalopod's weapon was its overwhelming size and crushing power. In response to the threat of cephalopods, many trilobite species evolved the ability to enroll, curling their bodies into a tight, armored ball, much like a modern pill bug. This protected their soft undersides and made them a difficult shape for a predator to manipulate. However, fossil evidence suggests that Cameroceras was well equipped to handle this. The numerous tentacles could manipulate the enrolled trilobite, turning it until the beak could find a weak point in the shell, or simply apply enough pressure to shatter the calcite plates. This interaction left its mark on the fossil record. Paleontologists often find trilobite remains with specific bite marks or healed injuries that match the shape of a cephalopod beak. These successful escapes show that the relationship was not always fatal, but a constant evolutionary race. As Cameroceras grew larger and more efficient at hunting, trilobites were pressured to evolve more complex burrowing behaviors, better camouflage, and thicker shells. It was a silent, generational dialogue between two ancient lineages. The abundance of trilobites provided the high-protein diet necessary for Cameroceras to maintain its massive metabolism and grow its multi-meter shell. In turn, the predation by cephalopods helped regulate trilobite populations, preventing any single species from over-consuming the benthic resources. This balance was the foundation of the Ordovician food web. It was a world where the predator was a drifter and the prey was a crawler, both playing their parts in the slow, rhythmic cycle of the ancient ocean. As we look upon a fossilized trilobite today, we see a creature that spent its life in the shadow of giants. Its form, the spines, the eyes, the thick shell, is a direct reflection of the world it shared with Cameroceras. The trilobite connection reminds us that no species exists in isolation. The giant orthocone was sculpted as much by the armor of its prey as it was by the water that carried it. While buoyancy allowed Cameroceras to hang weightless in the water, it required a specialized engine to navigate the vast distances of the Ordovician basins. This engine was the hypernome, a muscular, funnel-shaped organ located just below the head. Through the simple yet effective principle of jet propulsion, this organ transformed the animal from a passive drifter into a purposeful traveler. This chapter examines the fluid dynamics and muscular coordination that moved a giant of stone through a liquid world. The process of movement began within the mantle cavity, the spacious interior of the living chamber. Cameroceras would relax its mantle muscles, allowing oxygen-rich seawater to flow into the cavity and bathe its gills. To generate movement, the animal would then rapidly contract these muscles, sealing the entrance and forcing the trapped water out through the narrow tube of the hypernome. The resulting jet of water created an equal and opposite reaction, pushing the long, heavy shell in the opposite direction. It was a rhythmic, pulsing motion, a heartbeat of travel. The hypernome was highly flexible, capable of being aimed by the animal to adjust its course. By pointing the funnel toward the rear, Cameroceras could move forward. By angling it downward, it could lift its head. However, because of the immense length and rigidity of the orthoconic shell, this movement was built for stability rather than agility. The giant did not dart like a modern squid. Instead, it moved with a steady, momentum-driven pace. Each pulse of the hypernome sent the animal gliding through the water in a smooth, linear trajectory, a motion as unhurried as the drifting of a cloud. Efficiency was the hallmark of this system. Because Cameroceras was neutrally buoyant, it did not need to use its jet propulsion to stay afloat. Every bit of energy expended by the hypernome went directly into horizontal movement. This allowed the giant to patrol hundreds of square kilometers of the deep shelf with minimal metabolic cost. In the nutrient-dense but vast Ordovician seas, being an energy-efficient traveler was the key to reaching such colossal proportions. The physics of the long shell also played a role in its locomotion. The tapering cone acted as a stabilizer, preventing the animal from yawing or rolling during its pulses of movement. Like an arrow fletched by gravity and buoyancy, Cameroceras was designed for straight-line travel. This made it a perfect, long-distance cruiser, capable of moving from one trilobite-rich meadow to the next across the submerged continental interiors. The hypernome was the silent, pulsing motor that made this global distribution possible. As we visualize the giant in motion, we see the rhythmic contraction of the soft tissues at the shell's opening. A steady stream of water would emerge from the hypernome, creating subtle ripples in the clear brine. There was no turbulence, no splashing, just the quiet, powerful displacement of the sea. This movement was a part of the ocean's own rhythm, a pulse that resonated through the millions of years of the Ordovician. The hypernome reminds us that even the most massive creatures are bound by the laws of fluid dynamics. To move through the water is to engage in a constant dialogue with the medium itself. For Cameroceras, that dialogue was one of grace and persistence. Through the simple expulsion of water, the giant conquered the distance of the ancient world, proving that even a creature encased in stone could find the freedom of the open sea. The hallmark of Cameroceras is its staggering scale. In an era when most marine life was measured in centimeters, this cephalopod reached lengths that would not be seen again in the invertebrate world for hundreds of millions of years. It was the undisputed titan of the Ordovician. This chapter examines the physical dimensions of the species, moving past the realm of exaggeration to look at what the fossil record truly reveals about the size and mass of this ancient wanderer. Fossilized remains of Cameroceras shells, particularly the robust sifuncles and partial phragmicones, provide the data for these measurements. While the fragile nature of the shell means that complete, unbroken specimens are rare, conservative scientific estimates place the total length of the shell at approximately 6 meters, nearly 20 feet. Some larger specimens suggest the potential for even greater dimensions. When the soft body and tentacles are included, the animal occupied a space in the water column comparable to a modern delivery truck. Mass is as significant as length. A shell of such size, constructed of dense calcium carbonate, was remarkably heavy. However, because of the gas-filled chambers we explored in previous chapters, this weight was neutralized in the water. On land, a Cameroceras shell would weigh hundreds of kilograms. In the ocean, it was weightless. This physical paradox allowed the animal to grow without the structural limitations that gravity imposes on land-dwelling creatures. The only limit to its size was the availability of food and the time required to secrete the necessary minerals. The diameter of the shell also tells a story of immense power. At its widest point, the aperture of the living chamber, a mature Cameroceras could measure nearly a meter across. This provided ample space for a massive buccal mass and powerful muscles. The tapering of the shell was gradual, creating a long, elegant needle that could cut through the water with minimal resistance. This aspect ratio made the animal a stable platform, resistant to the buffeting of currents, even as its total surface area increased. Growth was a lifelong journey. Cameroceras did not reach a final size and stop. Instead, it continued to add chambers as long as it lived and remained healthy. This means that within a single population, there was a vast range of sizes, from small juveniles only a few centimeters long, to the ancient multi-meter patriarchs of the deep shelf. The giant specimens we find in the fossil record represent the survivors, individuals that successfully navigated the tides and the competition of the Ordovician for decades. The scale of Cameroceras had a profound effect on the ecosystem. Its mere presence altered the behavior of other species, creating a landscape of fear, where smaller organisms sought the cover of reefs and mud. Its size also meant it had few, if any, natural predators once it reached maturity. It was a creature that had outgrown the dangers of its world, achieving a level of physical security that allowed it to move through the oceans with the slow, unbothered confidence of a true apex predator. As we reflect on these dimensions, we see a creature that pushed the boundaries of what was biologically possible for a mollusk. Cameroceras was not just a large animal, it was a testament to the productivity of the Ordovician seas and the efficiency of the cephalopod blueprint. It stands in the fossil record as a reminder that the ancient past was a world of giants, where the simple combination of water, minerals and time created monuments of living stone. The world of Cameroceras was a planet of water, vastly different from the map we know today. During the Ordovician period, the Earth's tectonic plates were positioned such that most of the continental land masses were clustered in the southern hemisphere, leaving the northern hemisphere as a nearly unbroken expanse of deep ocean. The giant orthocones did not inhabit the deep abyssal plains of the open Panthalassic Ocean, but rather the shallow, sun-drenched seaways that flooded the low-lying continents. This chapter maps the ancient corridors through which Cameroceras drifted. Three major landmasses, Laurentia, Baltica and Siberia, sat near the equator, separated by the Iapetus Ocean. Much of what is now North America, Northern Europe and Russia was submerged under shallow epicontinental seas. These seaways were rarely more than 200 meters deep, creating a warm, stable environment that stretched for thousands of kilometers. These were the highways of the orthocone, a world without the barriers of modern mountain ranges or land bridges, allowing Cameroceras and its kin to achieve a nearly global distribution. The chemistry of these seaways was dictated by their isolation from the deeper, colder polar waters. With no ice caps at the poles for much of the period, there was less vertical mixing of the ocean layers. This resulted in a stratified sea, where the shallow shelves remained consistently warm and saturated with calcium carbonate. This calcite sea state provided the ideal conditions for a creature that required massive amounts of mineral wealth to construct a multi-meter shell. Cameroceras was, in many ways, a biological product of this specific geological moment. Tides and currents in these vast, shallow basins moved with a different rhythm than our modern coastal waters. Without the deep water trenches to funnel them, the tides moved in slow, sweeping pulses across the flooded continental interiors. These currents acted as a conveyor belt for Cameroceras. By adjusting its buoyancy and catching these slow-moving masses of water, the giant could travel from the shores of Laurentia to the edges of Baltica with minimal effort. It was a traveller of a borderless world, drifting across the submerged heart of the planet. The fossil record confirms this wide-reaching geography. The remains of Cameroceras and closely related endocerids are found today in the limestone quarries of New York, the cliffs of Estonia, and the mountains of China. These far-flung locations were once parts of a continuous marine province. When we find a Cameroceras fossil today, we are looking at a creature that might have spent its decades-long life crossing an ancient ocean that has since vanished entirely into the Earth's mantle through subduction. As the continents slowly drifted toward one another, these seaways began to narrow. The closing of the Iapetus Ocean would eventually change the currents and the temperature of the water. but for tens of millions of years, the paleogeography was one of perfect, stable openness. It was a world of interior oceans, where the horizon was always a line of blue water meeting a blue sky, and the giants below moved through a liquid empire that spanned the globe. The immense length of Cameroceras presented a unique challenge in the physics of the ancient sea, the struggle between a heavy tail and a heavy head. While the gas-filled chambers provided the necessary lift to stay afloat, they did not automatically ensure the animal remained level. Because the living tissue was concentrated at the front, the long, hollow shell had a natural tendency to tilt upward, leaving the predator bobbing vertically in the water. To solve this, the species evolved a sophisticated system of internal counterweights, known as cameral deposits. Cameral deposits were heavy accumulations of calcium carbonate that the animal secreted within the oldest, smallest chambers at the rear of the shell. Unlike the thin, light septa, these deposits were dense and solid. By adding weight to the very tip of its cone, Cameroceras could effectively pull its tail down, balancing the mass of the living body at the head. This was a masterwork of biological engineering, using the same mineral that provided protection to also provide the perfect center of gravity. This balancing act transformed the giant into a stable, horizontal platform. In the calm, low-energy environment of the Ordovician deep shelf, a horizontal posture was essential for efficient hunting and movement. It allowed the animal to scan the seafloor with its eyes and tentacles, while maintaining a streamlined profile for jet propulsion. Without these cameral deposits, the giant would have been a clumsy, upright drifter, unable to direct its power with the precision required of an apex predator. The deposition of these minerals was a slow, controlled process. As the animal grew and its living chamber became larger and heavier, it would simultaneously thicken the deposits in its rear chambers. This ensured that the equilibrium remained constant throughout its life. It was a dynamic balance. The animal was essentially a living scale, constantly adjusting its internal weight to match the changing dimensions of its own body. This allowed Cameroceras to maintain its grace, even as it reached lengths of 6 meters or more. In the fossilized remains we find today, these deposits are often clearly visible. When a shell is cut in a longitudinal section, the rear chambers appear filled with solid, crystalline stone, while the forward chambers remain hollow or filled with secondary sediment. These deposits are the silent evidence of the animal's life of weighted flight. They show us that every millimeter of the shell had a purpose. Every chamber was either a balloon of gas or a ballast of stone, tuned to the density of the surrounding brine. The gravity of the shell was not a burden to be overcome, but a force to be managed. Through the use of cameral deposits, Cameroceras turned the inherent weakness of a long, straight shell into a functional advantage. It became a creature of perfect poise, a horizontal needle of life suspended in the blue. This stability allowed it to inhabit the quietest corners of the Ordovician world, moving with a silent, level authority that defined the peak of cephalopod evolution. The shell of Cameroceras was more than a shield. It was a chronological ledger. Every day of the giant's life was recorded in the slow, persistent secretion of aragonite. Because the shell grew incrementally, adding new material to the aperture while sealing off the past with septa, it became a biological archive of the Ordovician environment. This chapter explores the steady, rhythmic expansion of the orthocone and the secrets held within the layers of its stony home. Growth began at the leading edge of the mantle, where specialized cells extracted calcium and carbonate ions from the seawater. This deposition occurred in microscopic layers, often reflecting the daily and seasonal cycles of the ancient world. In some well-preserved specimens, these growth lines are visible under magnification, appearing as delicate ridges on the shell's exterior. These lines suggest that Cameroceras grew in pulses, with periods of high metabolic activity followed by moments of rest. These rhythms were the heartbeat of the species, translated into the medium of stone. The most significant markers of time were the septa. Each internal wall represented a distinct stage in the animal's maturity. When the soft body grew too large for its current living chamber, it would move forward, and a new septum would be built. By counting these chambers, paleontologists can estimate the age of an individual, much like counting the rings of a tree. A full-grown Cameroceras possessed dozens of these chambers, indicating a lifespan that likely stretched across decades. It was a life of patient, linear progression. The chemistry of the shell also changed in response to the environment. The ratio of oxygen isotopes within the aragonite acts as a prehistoric thermometer. When the Ordovician seas warmed, the shell recorded a specific chemical signature. When the water cooled, the signature shifted. These chemical memories show that Cameroceras lived through a remarkably stable period of Earth's history, yet it was sensitive enough to record even the slightest variations in the ancient climate. Its shell was a living instrument, tuned to the temperature of the world. Feeding also left its mark on the rhythms of growth. A period of abundant prey, perhaps a seasonal migration of trilobites, would allow for a rapid expansion of the living chamber and the thickening of the shell walls. Conversely, during leaner times, the growth lines would cluster closer together, reflecting a slowed metabolism and a conservation of energy. The shell was a mirror of the animal's success, a physical manifestation of every calorie consumed and every mineral processed in the silence of the deep. As the animal aged, the rate of growth gradually slowed. The final chambers of an ancient Cameroceras are often shorter and more closely spaced than those formed during its midlife prime. This senescence marks the transition from a period of rapid expansion to a period of maintenance. The giant had reached the limits of its design. It had become a monument to its own endurance, a 6-meter needle of history that had witnessed the slow-motion evolution of the seafloor for a third of a century or more. In the fossils we find today, these rhythms are frozen. We see the start of a life in the tiny, pointed apex of the shell, and its conclusion in the massive, wide aperture of the adult. Between these 2 points lies a lifetime of steady, rhythmic work, a story of a creature that built its own history out of the sea itself, one molecule at a time. In the vast, blue-grey expanse of the Ordovician Sea, light was not the only source of information. For Cameroceras, the water itself was a medium thick with chemical signals, the scent of prey, the presence of kin, and the changing salinity of the currents. To interpret this invisible landscape, the giant utilized a sophisticated system of chemoreception. This was a world experienced not just through the eyes, but through the delicate sensing of molecules, allowing the predator to navigate a world that was as much a map of odors as it was a map of light. Located near the base of the tentacles and around the eyes were specialized sensory organs known as rhinophores and olfactory pits. These were small, recessed areas lined with highly sensitive chemoreceptive cells. As Cameroceras moved, water was channeled into these pits, where the animal could smell the brine in real time. This chemical sense was incredibly acute, capable of detecting a single drop of organic matter diluted in millions of liters of seawater. For a predator in an ocean without modern competitors, this was the ultimate tracking system. The scent of the Ordovician was dominated by the metallic tang of minerals and the organic musk of the benthos. A distant colony of crinoids, a molting trilobite, or a decaying organism on the seafloor would all release chemical plumes that drifted with the slow currents. Cameroceras would tilt its head, sampling the water to determine the direction of the plume's source. By comparing the concentration of chemicals between its left and right sensory pits, it could triangulate the position of its target, moving with a steady, inevitable focus toward its next meal. This chemical awareness also served as a vital communication tool. In an era before the evolution of complex sound-producing organs, the giants likely communicated through the release of pheromones. These chemical messages could signal readiness for mating or mark a territory within a specific seaway. Because the Ordovician oceans were so stable and the currents so predictable, these chemical signals could persist for long periods, creating a slow-motion social network that linked individuals across the vast, submerged continental shelves. Chemoreception also provided an early warning system for environmental changes. Cameroceras was highly sensitive to the pH and oxygen levels of the water. If a current shifted, bringing in colder, more acidic water from the deeper basins, the animal's sensory pits would detect the change long before the physical effects were felt. This allowed the giant to adjust its depth or direction, seeking out the optimal conditions for its carbonate-heavy metabolism. It was a creature in perfect chemical harmony with its environment. As we visualize the giant drifting through the deep, its tentacles are never truly still. They are constantly twitching, flicking and sampling, drawing the water toward the sensory pits in a rhythmic, invisible dance. This was the invisible sight of the orthocone, a way of knowing the world that was both intimate and profound. It reminds us that for Cameroceras, the ocean was not a void, but a rich, complex library of information, where every pulse of the tide brought a new story to be read by the senses. The chemical world of the Ordovician was one of stillness and clarity. In this environment, Cameroceras reigned not just through size, but through its ability to perceive the very essence of the sea. Through its sensory pits, it was connected to the life of the benthos and the movement of the tides, a silent, sensing giant that understood its world one molecule at a time. Beyond the churning tides of the shallowest coasts lay the true domain of Cameroceras, the deep shelf. This was an environment of profound tranquility, situated far enough below the surface to be shielded from the chaos of storms, yet high enough above the abyssal floor to remain bathed in the gentle blue light of the sun. In this middle world, the water moved in slow, predictable sheets, and the temperature remained nearly constant. This chapter explores the meditative stillness of the habitat, where the giant spent the majority of its long life. The deep shelf was a low-energy environment. In our modern world, we often think of the ocean as a place of crashing waves and powerful surges, but for Cameroceras, the sea was a liquid suspension of perfect calm. The silt on the seafloor was so fine and undisturbed that it felt like velvet to the touch. Because the water was so deep, the influence of the wind was lost, and the only movement was the slow, rhythmic displacement of the global tides. This stillness allowed the orthocone to maintain its horizontal poise with almost no effort, drifting like a ghost through a world without wind. This environment was also a sanctuary of light. While the shallow reefs were bright and high contrast, the deep shelf was a realm of soft, diffused indigo. The red and yellow wavelengths of sunlight were filtered out by the water above, leaving only the cool blues and greens to illuminate the crinoid forests. To a creature with the pinhole eyes of Cameroceras, this was a landscape of extreme clarity. There was no murky runoff from terrestrial rivers to cloud the view. The water was as transparent as the air, allowing the giant to see the outlines of the seabed from dozens of meters above. The ecological stability of the deep shelf was the secret to the giant's longevity. In this stable world, resources were predictable. The marine snow, a constant drizzle of organic particles from the upper layers, nourished a complex community of filter feeders that, in turn, supported the trilobite populations. Cameroceras did not have to contend with the sudden temperature shifts or the seasonal fluctuations that define modern marine life. It lived in a state of eternal autumn, a perpetual twilight, where the only measure of time was the slow accumulation of carbonate on its shell. This tranquility also dictated the animal's behavior. There was no need for the frantic, high-speed maneuvers of modern oceanic predators. In the calm of the deep shelf, Cameroceras could afford to be a methodical, unhurried hunter. Its movements were as silent as the water itself, and its presence was a natural extension of the environment. The giant was not a disruption of the peace, it was the embodiment of it. It moved through the indigo light with the weight of geological time, a silent monarch in a kingdom of absolute stillness. As we visualize the orthocone in this setting, we see the true nature of the Ordovician. It was a world that had mastered the art of endurance. The deep shelf was a place where life could reach massive proportions simply because it was never interrupted. In the silence of the blue, the only sound was the faint, rhythmic pulse of the giant's hypernome, a soft, wet heartbeat echoing through a world that was content to remain unchanged for millions of years. The profound stability of the Ordovician world was not eternal. As the period drew toward its close, the global climate began a slow, inexorable shift that would forever alter the habitat of Cameroceras. Far to the south, the massive supercontinent of Gondwana drifted over the South Pole, providing a foundation for the accumulation of ice. This was the beginning of the Hernantian glaciation, a geological event that signaled the end of the calcite sea era. This chapter examines the first subtle signs of a world growing cold. The first change was felt not in the temperature of the water, but in its depth. As the ice sheets on Gondwana grew, they began to lock away vast quantities of the planet's water. The global sea level, which had been at an all-time high for millions of years, began to drop. For a giant that relied on the expansive, shallow, epicontinental seas, this was a critical turning point. The vast highways of the submerged continents began to drain, retreating toward the edges of the continental shelves and shrinking the world of Cameroceras hectare by hectare. In the deep shelf, the cooling was gradual. The warm, tropical currents that had sustained the giant's metabolism for decades began to lose their strength. The water became denser and more oxygen-rich, but it also held less of the dissolved calcium carbonate needed for shell construction. The carbonate factory of the Ordovician began to slow its production. Cameroceras fossils from this transition period sometimes show evidence of physiological stress, slower growth rates and thinner shell walls, as the animals struggled to harvest minerals from a changing ocean. The biological community was the next to react. The crinoid meadows and trilobite populations that flourished in the warm shallows were forced to migrate or face local extinction as their habitats vanished. The predictable food web that Cameroceras had dominated for eons was fracturing. As the water receded, the competition for the remaining deep shelf space intensified. The giant, once an unbothered monarch, now shared its shrinking territory with a more crowded and desperate array of species, all compressed into narrowing corridors of habitable water. This shift also altered the ocean's chemistry. The cooling of the poles initiated a new pattern of global circulation, bringing cold, nutrient-rich bottom waters up to the surface. While this upwelling initially provided a surge of life for smaller planktonic organisms, it also disrupted the stratified calm that Cameroceras preferred. The quiet, indigo twilight of the deep shelf was replaced by more turbulent, unpredictable conditions. The stable, predictable rhythms of the previous 30 million years were giving way to the chaos of a planet in transition. As we observe the final generations of Cameroceras, we see a species at the edge of its ecological limit. It was a giant built for a world of warmth and limitless space, and it was now living in a world of contraction. The ice in the south was a silent, growing presence, a geological force that no amount of biological armor could deflect. The era of the great orthocone was approaching its sunset, not through the arrival of a faster predator, but through the slow, chilling breath of the Earth itself. The story of Cameroceras reaches its conclusion in the silent layers of the late Ordovician limestone. As the Hernantian glaciation reached its peak, the environmental pressure on the giant orthocones became insurmountable. The vast, shallow seas that had served as their kingdom for millions of years finally withdrew from the continental interiors, leaving behind only the sediment of their passing. This chapter examines the final fossilized footprints of these titans and the geological evidence of their departure from the world's stage. In the final strata where Cameroceras is found, there is a noticeable shift in the fossil assemblage. The diversity of the benthic community, the trilobites and brachiopods, begins to plummet. As the water grew colder and shallower, the specialized niches that supported the giant's prey vanished. The fossilized shells of the last Cameroceras are often found in lag deposits, concentrated layers of shells that were swept together by the retreating tides. These sites represent the closing of a door, a final gathering of a lineage that no longer had a place to drift. The extinction of the large endocerids was not a sudden catastrophe, but a slow displacement. As the sea levels fell, the water column that Cameroceras required for its massive 6-meter shell simply ceased to exist in many parts of the world. A creature of such immense length and rigid structure could not adapt to the turbulent, shallow coastal environments that remained. The very architecture that had made it the master of the deep shelf became its undoing in a world of receding shorelines and crashing waves. Chemical analysis of these final layers reveals a world in flux. The calcite sea conditions were replaced by an aragonite sea state, and the carbon cycle of the planet was undergoing a massive reorganization. For a species that invested so much metabolic energy into the construction of a carbonate fortress, these chemical shifts were likely fatal. The last generations of Cameroceras were smaller, their shells less robust, reflecting an organism that was literally running out of the materials and the time needed to sustain its giant form. As we look at the very top of the Ordovician strata, the straight-shelled giants disappear entirely. They are replaced by smaller, more versatile cephalopods, lineages that were more mobile or better suited to the changing pressures of the rising and falling seas. The vacancy left by Cameroceras was profound. The oceans would not see an invertebrate predator of this scale for eons. The final fossils are often fragmentary, worn down by the same ancient currents that once carried the living animals, eventually buried under the new sediments of a colder, different world. The disappearance of Cameroceras marks the end of the first great age of marine giants. It was a casualty of the planet's shifting climate, a testament to the fact that even the most successful and dominant species are bound to the stability of their environment. When the calm of the deep shelf was broken, the giant broke with it. What remains is the stone, the heavy, straight needles of the orthocones locked in the limestone, waiting to tell the story of a time when the earth belonged to the silent drifters of the deep. The dawn of the Silurian period brought a new architecture to the world's oceans. As the great ice sheets of the Hinantian glaciation retreated and the sea levels rose once more, they flooded a landscape that had been fundamentally reset. The era of the straight-shelled giants had passed, but the legacy of Cameroceras was not lost. It lived on in the resilient lineages of smaller nautiloids that survived the cold, and in the very limestone that now armoured the planet's crust. This final chapter observes the echo of the orthocone in the millions of years that followed. The Silurian seas were characterized by the rise of new reef-building organisms and the first significant diversification of jawed vertebrates. In this more crowded and competitive world, the strategy of the massive, rigid orthocone was replaced by a drive toward maneuverability and speed. The descendants of the nautiloids began to experiment with coiling their shells, a design that condensed their mass and made them more agile. These coiled forms, the ancestors of the ammonites, would eventually dominate the water column, but they carried with them the same internal chambers and siphuncle systems pioneered by Cameroceras. The physical remains of Cameroceras itself became a part of the Earth's geological foundation. The massive shells, settled into the silt of the Ordovician basins, were slowly transformed into stone. Over hundreds of millions of years, these limestone beds were lifted by tectonic forces, forming the cliffs and quarries of the modern world. Today, when we find a fragment of a Cameroceras shell, we are touching a piece of the Ordovician seafloor. The calcium carbonate harvested from the ancient brine remains with us, a permanent record of a world that existed long before the first dinosaur. Beyond the stone, the story of Cameroceras serves as a vital chapter in the history of life. It represents the first time the Earth's oceans supported a truly massive apex predator. It proved that the cephalopod body plan, with its tentacles, beak, and buoyancy-controlled shell, was capable of achieving global dominance. The giant was a biological pioneer, testing the limits of size and stability in a fluid environment. Its success for tens of millions of years demonstrates the power of a specialized design in a stable world. The ghost of the orthocone is still visible in the modern ocean. The Nautilus, drifting through the deep reefs of the Indo-Pacific, is a living relative that utilizes the exact same principles of hydrostatic equilibrium and chambered growth. Though much smaller and coiled for protection, the Nautilus is a direct link to the world of Cameroceras. To watch a Nautilus drift through the indigo light is to see the phantom movements of its giant ancestors, a slow-motion grace that has survived 5 mass extinctions. As we conclude our journey through the Ordovician deep, we are left with a sense of the ocean's immense patience. The story of Cameroceras is not one of violence or drama, but of enduring rhythm. It is a story of how the sea builds its monuments, and how, in the fullness of geological time, it eventually reclaims them. The giant straight shells are gone, but the silence and the blue of the deep shelf remain, holding the memory of the time when the titans moved weightless through the ancient dark. The documentary of the orthocone ends as it began, in the stillness of the water. The fossils remain locked in the strata, silent witnesses to a mastery of the sea that was both absolute and fleeting. They remind us that we are part of a planet that dreams in stone and moves in tides, a world where the giants of the past are never truly lost, as long as the sea continues its rhythmic pulse against the shore.